Today's lesson is going to be on swapping nodes in a linked list. Now, if you haven't watched my previous video on linked lists, you really should because it provides the context for this video, and I'll put a link to it in the description and maybe even like a little link in the video here at this time now. Now, if you have created a doubly linked list, so meaning it links forwards and backwards, then you're going to have something that looks like what's on the screen right now. So what we can look at is you can say, how do you swap items in the node? And I guess one thing that a lot of people will try and do is they will actually just try and swap the data. So what they'll do is they'll get a temp variable. They'll just take one of the numbers, move it out, swap this over, like move it over like so, and then swap this back like so. And they'll say, aha, I swapped the nodes. Well, the problem with that is that you actually haven't swapped the nodes. You only swapped the data. But essentially, that's the same thing anyways, right? So in the example that I've been giving, I've been using just straight up integers, which is fine, and it makes this process really easy. But what if these nodes didn't just contain integers, right? What if they contained like whole video files or something like that, right? Well, swapping the data in the nodes might actually be like a lot of work, right? And it could actually be quite an expensive operation because it could require a lot of, there could be a lot of different elements. It could be whole records of movies or, and things like that, right? So you don't necessarily want to just go and swap the data. Instead, what you'd like to do is actually swap just the nodes themselves by rearranging their links. Right? And in this example, we're going to have to be able to go forwards and backwards, which complicates things a little bit, but it also makes things a little bit easier for us too. Now, I'm going to show an example of just one of part of the operation that we're going to do, and then this is actually for my students, so I'm going to be leaving it open for them to finish the rest of the operations. Okay, so let's take a look here. And go to Eclipse. Okay, so we have our basic linked list here, and I've tested its functionality by pushing numbers from 1 to 10 and then displaying and then repeatedly popping numbers off one at a time and then showing the list and then trying to pop from an empty list. Right, and you can see everything seems to be working correctly. Right, so we don't actually need to look at the popping here. So we're going to just take that away. Instead, what we're going to do is we're going to say list.swap, and then we are going to display again. All right, and that should be list.display. All right, now before we can swap, right, well, what are we going to swap? Well, in this particular example, what I'm going to do is I'm going to swap just two specific numbers, and I'm going to assume that the list is just sequential, there's only one instance of every number in the list, right? So that way it'll make it easy to find the numbers, and then after that, the swapping is relatively simple. But nonetheless, you could actually make it just be able to swap out like by node location, and it's not that hard to modify the code for that. All right, so what we're going to do is we're going to say swap something like 110. Okay, and so in this example, I want to swap the numbers 1 and 10 in the list. Okay, so how do we do that? Well, the first thing we're going to have to do is we're going to have to look for the numbers, so find the actual nodes there. All right, so let's take a look here. Like this. Okay, I just want to make sure I'm actually in this. Okay, so we're going to go. Now, the key to this is going to be writing a method called find. Okay, so we're going to say public node find int data. And what this method is going to do is it's going to look for just the very first occurrence of that data item. All right, so what we will do is we will say node temp is equal to first, while temp does not equal to null, so meaning it did not go to the end of the list. We are going to say if temp.getData so is equal to, let's actually not call it data, we'll just call it target. Okay, so is equal to the target. So if the data we're looking for is equal to the target, we are going to return temp, right? And then if it doesn't find it, then what we will do is we will say temp is equal to temp dot get next to move to the next node. Now, if we manage to get through the whole list without ever finding that number, that means we just return null. All right, and we can test this out first. So let's take away the swap here, and we'll just see what happens here. So we'll say list.find. Okay, and we will have to do a print. We'll just print this out to show where it is. Okay, instead of a target, we'll just say look for a 1. Right, and we will look for the 1, the 10, and let's look for a number that's not in the list and see what happens. So an 11. All right, so we got some memory address here, another memory address, and then null. All right, and that actually looks correct because we are actually just looking for memory addresses. Hard to know if that's actually the memory address where it is, but I think it looks right, and we can assume it is for now until we have reason to think it's not. Okay, so what we're going to do is add another method. Okay, so we're going to say public. Now for swapping, you don't actually have to return anything, so swap. And then we're going to say int number 1, int number 2. Okay, so we are looking at 2 specific numbers to swap. All right, now the first thing is we're going to have to say node, and we will call it just node1 is equal to find number 1. So we're going to say find number 1 in the list. Okay, then we're going to say node2 is equal to find number 2. Great. Now at this point, what we want to do is we want to make sure that they've actually been found, but we can assume for now that they are. Now that's not actually a perfect assumption. So let's just cover it. Say if node1 is equal to null, okay, or node2 is equal to null. We can just cover it here. Actually, there's a better way to write this. If node1 does not equal to null and node2 also does not equal to null, then we're going to go into our algorithm here. Right? So what it is that we don't want node1 or node2 to be null. Right? If either one is null, then there's no point in swapping because it doesn't make any sense to do the swapping. Now, the next thing we have to do is we have to actually find their relative position to each other, because the order of operations, so the order of things that we're going to do to swap them, depends on whether node 1 is on the left side of node 2 or node 2 is on the left side of node 1. All right. Okay, so there's also something I should add here, I just thought of, and it's that node 1 does not equal to node 2. Right? So if you said to swap 2 of the same nodes, then there's no point in doing anything else. Okay, so it's the first one is not null, the second one is not null, and the first one is not the second one. Then move ahead. Okay, so how do we know if they are in the correct position? So what we're going to do is we are going to say Boolean correct relative position is equal to, and what we're going to do is we're going to say the correct relative position at first is equal to false. Okay, that they are not in the correct position. Now, what I'm going to do is I'm going to say int temp or node temp is equal to node 1. So we're going to start at node 1, and then I can say while temp does not equal to null, then what we are going to do is we are going to say if temp is equal to node 2, then correct relative position is equal to true. All right. So what that does is it sets temp to be node 1. right? So right here, we have set temp to be node 1. And then what it does is it says, okay, temp's not null, so it shouldn't be null because if it's in here, it's not going to be null. Now, if temp is equal to node 2, which it should not be on the first iteration, then you're going to set the correct relative position to be true. Now, that's probably not going to happen because, well, it can't happen if we're in here. Then we're going to say temp is equal to temp dot get next. All right, so we're just going to move to the next one. Now, if the next one, obviously, let's say it's not null, and then we go check. If it's node 2, then the correct relative position will be set to be true, and then it'll actually keep moving to the next one, and so on and so forth. But once the correct relative position is set to be true, then it can never be set to be false. And to speed things up a bit, what we could do is we could actually just break. So if we ever find node 2, the following node 1, then we don't have to look anymore. If it is correctly in the relative position. Okay, so what that means is that if this is the case, then node 2 is on the right-hand side of node 1. Okay, now if we ever get to the end of the list without doing this, that means that they are not in the correct relative position. So what we need to do is we can say if not correct relative position. So if things are not in the correct relative position, then what we need to do is swap them. So again, what we can just say is node temp is equal to node 1. Node 1 is equal to node 2. Node 2 is equal to temp. Now, a lot of people might ask at this point, they'll say like, well, didn't you just create like 2 different nodes here? Oh, actually, I don't have to, because I don't need to. I can just reuse that temp node. Okay, let's say, well, didn't you just swap these 2 nodes? Well, no, I didn't swap the nodes. I just swapped the names of the nodes. All right, so now node 1. Okay, so let's go to our diagram here. Okay, so we'll go to our diagram here, and let's say, for instance, node 1 is here. All right, and node 2 is here. Okay, now all we did is we actually just swapped the names of the nodes if they're not in the correct position, right? So what I'm doing is I'm saying, okay, take this node, move it over here, and take this node and move it over here, and basically put them back in the correct position. All right, now the way I've drawn it is that originally it is actually in the correct position. So we're going to have node 1, node 2, and everything looks good. Okay, so now we know that node 1 is always on the left-hand side of node 2, which is important because our future algorithms depend on us knowing that node 1 is on the left side and node 2 is on the right side. Okay, so we are going to go and take a look here, and let's see. Let's say in our example, now like I said, there's going to be many different situations for this, and it's going to take a little bit of work to work them all out. But we are going to try and swap 1 and 10. All right, so we're going to try and run the swap algorithm, and then display, and we're going to try and swap 1 and 10. Okay, now what we'll say is we will say in this particular situation, if node 1 is equal to first, so it's the first item in the list, and node 2 is equal to the last item in the list. All right, so if node 1 is the first item in the list and node 2 is the last item, then how do we do that? Okay, so we got to look at moving these nodes around. Okay, so we're going to say, okay, so we got to move these references around. Now the problem is if we ever dereference something, it's going to be really hard to re-reference it. All right, so sometimes what we might have to do is put down some node markers, just temporary variables names, just to hold those spots so we have ways of referring to nodes still. All right, so what I can do is I want to take this number 2 node, and I want to be able to point it so that when it goes backwards, it's going to point to the 10. All right, so how do I do that? Well, the name of this number 2 node is first.next or first.getNext. So what I can say is first.getNext, or instead of, well, I guess it would work, but we'll say node1.getNext. Okay, that's the number 2 node. Okay, so then what I can do is I can say set previous. So I can set its previous pointer to node 2. All right, so I can say node 1 get next, set previous back to node 2. That seems like a lot, I know. All right, so node 1 set next, or get next, that's this number 2 node. We want to set its previous pointer, or previous reference, okay, to be node 2. So now this one is going to be referring to this number 6 node. It doesn't actually matter in this case. I only have 6 nodes, but it'll be referring to the last node there. Okay. Similarly, what we want to do is we want to make the number 5 node here point back to the number 1 node, or point forward to the number 1 node. Okay, so what we will do is the name of the number 5 node could be called node 2 get previous. Okay, so we're going to say node 2 get previous. Okay, and then we are going to say dot set next to be node 1. Okay, so node 2 get previous and go to set next. So node 2 get previous, that's this node, set its next reference. All right, that's that one, and we're going to send this back to node 1. Okay, so now if we looked at the list, in the forward direction, it would go 1, 2, 3, 4, 5, but the 5 node would go back to the 1, and so it would actually go in an infinite loop. And in the reverse direction, it would go 6, 5, 4, 3, 2, and the 2 would go back to the 6, and that would also go into an infinite loop, which is not really what we want. Okay, so what we want to do is we want to move, what if we moved the first reference to the number 6 node? All right, so if we said this item here now moves over here, we label this one as being first. All right, so if we went first, then we'd go first null. Okay, but we could actually just fix that, and we could say, so first let's move it over. So first is equal to node 2, right? And then we could say first dot set next. Okay, now here's the problem. Where do we set it to? Well, let's take a look at our diagram here. First dot set next needs to go to the number 2 node. Well, is there a name of a number 2 node? Yes, it's node 1 dot get next. Okay, so node 1 dot get next. All right, so first dot set next to node 1 get next. So first set next to be node 1 get next. All right, so we're going to go all the way to here. And actually, that's not correct. This one, first set next to be node 1 get next, which is the number 2 node. All right. So now in the forward direction, we would have first going to 6, and then it would loop to 2, 3, 4, 5, and then go to 1, which is correct. And now the number 1 node needs to go to null. So we will say node 1 dot set next to be null. All right, let's go take a look at our diagram here. Node 1 set next is set to be null, so now node 1 is not going anywhere. And in the forward direction, it says 6 going to 2, then 3, then 4, then 5, going to 1, and then to null. So in the forward direction, it's fine. What about the reverse direction? So reverse direction goes 6, starting at last, then to 5, then to 4, then to 3, then to 2, and 2 leads back to 6, and so we're still in an infinite loop in that direction. Okay, so what do we do with that? We gotta try and loop it back now. Okay, so what we need to do is we can say, well, what if we move last over to the number 1? So take this last and move that over here. Okay, so now last is pointing at node 1. Let's go code that. Last is equal to node 1. All right, and then what do we do? Okay, let's take a look. Now, if we did this, then it would just go last and 1 would go to null. So what we have to do is we have to send node 1 over to the number 5 node, right? And we can do that because the number 5 node is still node 2 get previous. So we can say node 1 dot set previous to be node 2 dot get previous. Okay, so node 1 set previous to be node 2 get previous. So we have node 1 set previous, that's this one, to be node 2 get previous, which is the number 5 node here. So in the reverse direction now we've got 6, or sorry, going from last to 1. This is going to 5, then to 4, then to 3, then to 2, and the number 2 goes to the number 6, and number 6 needs to go to null. So we will say node 2 set previous to be null. All right, and I believe that actually is it. So let's take a look here. Now, as you can see, the diagram, which started off rather nice, actually has turned into a total mess. Okay, but I think it actually will work, okay, by just rearranging all these nodes. Okay, so hopefully it does work, and let's run it. Okay, so there we go. In forward direction is 1 to 10, reverse is 10 to 1. Now it goes 10, 2, 3, 4, 5, 6, 7, 8, 9, 1, and reverse goes 1, 9, 8, 7, 6, 5, 4, 3, 2, 10. Okay, so yes, it did work. Now here's the question though. Would this work if node 1 was not in the first position? What if node 1 was somewhere in the middle of the list, right? What if node 2 was not in the last position? What if node 2 was somewhere else in the middle of the list? Now, we already know that node 1 is on the left side of node 2, but the algorithm is obviously different if you're talking about nodes that are not on either side, on the ends of the list. What if node 1 is on the end, but node 2 is not on the end, or node 2 is the last, but node 1 is not? And then it actually gets further complicated. What if they're both in the center, but what if they are adjacent to each other? Right? So if you have the nodes that are adjacent to each other, then that algorithm is going to be different. If the nodes actually share a node between them, meaning that they are only one apart from each other, so there is a node, the node in between them is shared, then the algorithm is different. And then if there's 2 or more nodes between them, then the algorithm is basically the same for anything after that. Okay, but there are a lot of different cases that you're going to have to work on. And I'm going to leave it to the students here to actually complete this algorithm. Right? Now, there are some ways you can do it. You can actually just brute force every possible situation. That is a little bit tough, but there are ways to actually just, by using if statements and conditional things, to say, like, look, if it's here, then you're going to have to do this. If it's here, you have to do this. That's a little harder to work out, but the algorithm will be shorter and a little more efficient if you do it that way. I'll leave it up to my students to determine how they want to write it, either by brute forcing each possible situation or by trying to look at the different configurations and doing it conditionally. Anyways, that's it. If you have any questions, leave them in the comments of the video. Remember to like and subscribe. Thanks for watching, and I'll see you next video.